So folks, in our previous video we said that we're going to be solving the ODE x double dot plus 2x dot plus x equals 6 cosine t. So now we get to put all of our knowledge of solving linear ODEs to good use. In this case, we'll first solve the corresponding homogeneous equation. X double dot plus 2x dot plus x is equal to 0. And this has characteristic equation r squared plus 2r plus 1 is equal to 0, which factors to be r plus 1 quantity squared equals 0, which has two roots, but they are the same. R is equal to negative 1 with multiplicity 2. So what have we learned how to do? Well, in our most recent classwork, we learned that when we have repeated roots, that we can go ahead and give the solution, and this is the solution to the corresponding homogeneous equation, right? xh of t, that's the function set equal to 0, not the original non-homogeneous equation, and that would be c1, the general solution would be c1 e to the negative t plus c2, and then we need a second linearly independent solution, and we showed that this would also solve the corresponding ODE, and it's certainly linear independent, and you could check that by looking at the Wronskian. So now we've got our solution to the corresponding homogeneous ODE. Now we need what? Now we need one particular solution. We only need one particular solution because the superposition principle tells us that with that one solution and the corresponding family of solutions, we can reach all other solutions in the system, or to the problem. So we need one particular solution, we need to guess at it, and if we look at our forcing function here, our forcing function is this 6 cosine of t here. So our guess at y particular, or I guess we're calling it x here, our guess at the particular solution needs to take into account all linearly independent functions that show up in the forcing function, any linear combination of those, plus any of their derivatives. And of course that requires that the derivatives either eventually go to 0 or eventually repeat themselves, but we're okay with a cosine forcing function whose derivative would be a minus sine function and whose derivative of that would be a minus cosine function, which essentially gets us back to the same structure we had before. So we can use the method of undetermined coefficients on this, and our guess at the particular solution needs to take into account any linear combination of any linearly independent function that shows up in the forcing function, and all successive derivative terms, which get encapsulated when we represent our guess this way. So that's our guess at the particular solution. Again, folks, if you like, you could look up any table for the method of undetermined coefficients, and it would show that if your function is a cosine of t, then your guess at the trial solution should be a cosine t plus b sine t. But I think it's more important to think about it in terms of what I just said about all linear combinations of all linear independent functions that show up in the forcing function and any of their successive derivatives. And by that I mean not just the second derivative, but any derivative that could possibly show up through multiple iterations of those derivatives. Okay, so that's our guess at x of p. What we'll need to do is we'll need to calculate x of p dot. Taking the derivative of that gives me minus a times the cosine of t plus minus a times the sine of t, plus b times the cosine of t, and taking xp double dot would give me minus a cosine of t minus b sine of t. There I've got all the derivatives that I need. We'll plug this into original ODE. So when I do that, let's go up here. When we plug that into the original ODE, and this is going to be kind of lengthy, we will have minus a cosine t minus b sine t plus 2 minus a sine t plus b cosine t plus 1 a cosine t plus b sine t. Did I make it? Yeah, I've got enough room. And this needs to equal 6 cosine of t. So that looks like just an absolute mess, but this is my xp double dot here. This is my 2 xp dot, and this is my xp, and that fits with the original ODE that we set up, that you can see right here. So now what we're going to do, and I don't think we've done this before, we're going to collect together all of the sine terms and all of the cosine terms to enable us to solve for a and b. So if I were to group together all of the cosine terms, I would have for my coefficients a minus a from this cosine, a 2b from this cosine, and a 1a from that cosine. So all of these go with my cosines of t. And then if I were to collect together all of the sine terms, I'd have a minus b for that sine term, a minus 2a for this sine term, and a plus b for this sine term. All of this needs to equal 6 cosine t plus, and then usually we don't write this, but I will since it's our first time, plus 0 sine t. And from this we can make these same positioning equation arguments that we've been making all along. So I'm going to say then that minus a plus 2b plus a, which of course simplifies, needs to equal 6. So I get that 2b needs to equal 6, or b needs to equal 3. Likewise, I'll make the equivalent positioning argument for my sine terms, and this tells me minus b minus 2a plus b, which of course simplifies, needs to equal 0. So we get minus 2a needs to equal 0, or a is equal to 0. Now, we already had our x of p. Our guess for x of p was supposed to be a cosine t, so we find that it's 0 cosine t plus b sine t, so that would be 3 sine t, which it simplifies to be 3 sine t. So now I'm ready to give my general solution to this ODE. My general solution to the ODE is x of t equals c1 e to the minus t plus c2 t e to the minus t plus 3 sine t. And just to reiterate, this was our family of homogeneous solutions. Oops, I should call that x. This was our family of homogeneous solutions to the corresponding homogeneous ODE. And this is our one particular solution that we found through the method of variation of parameters to the original non-homogeneous ODE. And all of this together gives us our solution to the ODE. I'll see you in the next video.